university, and after that he had some postdoctoral appointment, one of them again in the Australian National University, and then he moved back to US, first as a lecturer in Boston University, then he was a research associate in Harvard, and starting from 2000 he became a faculty in University of Maryland, but more recently he had added another affiliation in Japan, in Tohoku University in Sendai. So his research has to do with the composition, structure, and evolution of the Earth and other terrestrial planets. He's an expert in neutrino geoscience and geoneutrino monitoring and topics like that they use to understand the structure of the interior of the Earth and other planets with similar structure. And today's talk is going to be about that, and the title is Earth's Composition and Power. William, the floor is yours.
Thank you very much, and thank you to all of you who have extended your home to my visit. Thank you very much. Okay, I'll be shaking, but it will stop after a little while. Okay, that might be even better. Good. So there will be two parts to my talk. I'll first start off talking about the silicate Earth and how I can use meteorites and rocks from the Earth to tell a story about the Earth's composition. I'll then transition to start talking about neutrinos to give you a little background to what neutrinos are, how I can use neutrinos to actually talk about the Earth, and then I will conclude showing that neutrinos can give me the same information that rocks can and can constrain the composition of the Earth. So I'll try and show you I can get the composition of the Earth two different ways as a piece of informational evidence. Remember which, okay. So I'm going to start off by talking about the rocky record or rock story. And this will actually talk about the rocky planets, and I particularly want to point out that in the beginning of the building of the solar system, we talk about a protoplanetary disk, and I want to emphasize through this talk that the nature of the disk is what ends up being the sun, and that the rocky planets are not the analogs of the protoplanetary disk. We have to derive their compositions independently. That's a very important feature. Next. I have learned over the decades that I have been biased by the meteoritic record. So I've recently written a paper where I tried to reveal these biases. And they can be very significant, so I'll talk a little bit about that. I think in all of our sciences, we can get biased in one direction or another. And then I want to emphasize that the chemical trends that I see in the rocks from the cosmos, the meteorites, and the rocks from the Earth tell a similar story, and I use them to define the composition of the Earth. So I very much appreciate history, and I just love the history of science. I've actually studied it over a long period of time. Copernicus, actually there was a Greek fellow, but Copernicus is often related to as the father of astronomy. Copernicus made a very simple observation that I want everybody to think about. If we were to elevate ourselves to be above this Earth, above the sun, and we stare down at our wonderful solar system, the one thing that will become obvious, oh my gosh, well, this is really interesting. All right, I'll point it here. The start of our solar system is generally perceived to be from a perturbation. Now, in this cartoonish type illustration, it reflects a supernova event. But today we can tell from the nuclear forensic information that's stored in meteorites that it was not a supernova. It was likely a burp, a gaseous moment of outflow from a Wolf-Rayet star, one of these big superstars. Okay, and that perturbation basically took apart a portion of a gas molecular cloud, and that itself then began co-rotating, collapsing, and began the process that we see emphasized here as 1 million years. Later, 2 million years, 3 million years. I like this diagram, not mine, but somebody else's. I like this diagram because of a couple of things. It illustrates the evolution of going from the perturbation, here a supernova event, to the formation down in the lower left corner of the planets orbiting our star. This works well for our system. This will work well for any and every exosystem. So we're still hanging out well above our star, looking down. What did Copernicus say? He says, you know, we spin on an axis, and that makes a day. He is actually the one to sort of note that. Oh my gosh, I'm not so good at this. I just want a simple pointer. Oh my gosh, I touched too many things. Simple pointer. One more back. I need to go back one. There. So here, the Earth rotates on its axis. I think of the Earth as a vehicle. And I'm going to use that analogy in a little while, because I'm going to tell you about how we're making a fuel gauge for this planet. Okay, but I'll leave that thought with you for a little bit. But if you think of it, we are on a fabulous spaceship, and we are rotating at a half a kilometer a second. We're going around the sun 30 kilometers a second. We're going around our galaxy at 230 kilometers a second. By the way, it takes about 250 million years to go around that black hole. And we've done it several times. Yes?
I always heard that the Earth is 4.5 billion years.
It is.
So what does it mean, 1 million years? So if you go back from here in this plot, it's 1 million years.
Yes.
So what does it mean, 1 billion years in this plot? In this graph here that you...
I know which one you're pointing at. What does it mean 1 million years?
What does it mean 4.5 billion years ago?
Okay, that's a very good question. So I'll try and place chronology or time into perspective. In fact, the first thing I have to point out, which I think is a very important illustration, I was born on September 1st, 1954. So now you know how old I am, 71 plus, okay? What you specifically know, and I don't mean to use a bad word or improper ideas, is you now know that there was a birth canal moment. Now, in my country, the United States, we sometimes argue that my birth was associated with the insemination when I was created at that point. But let us use the standard definition that everybody in this room uses. It's our birthday. Planets, like trees, don't have birthdays. You think about a tree. What would you call a tree's birthday? The time the seed was finally fertilized to get to go? The time the seed finally poked its little nose out of the ground to the dirt? Or the time the seed got maybe about this tall? We cannot give a good definition to the age of a tree. We cannot give a good definition to the age of the Earth in that sense. However, this is what we do. Oh, let's say we also have a difficult time with the age of the solar system. The age of the solar system is not the same as the age of the Earth. But given our inadequacies, we do make assumptions. The oldest thing we can date is called the calcium-aluminum inclusion. And we know it to be the oldest thing because we can't find anything older, and we've taken apart meteorites for decades now, And you'll get a Nature paper within a week if you found something truly older. What does this oldest piece of material that we can put our hands on, the calcium-aluminum inclusions, it represents the age at which didn't get sucked into the sun. So maybe the sun was already 50,000 or 100,000 or maybe even a million years, but unlikely. But the sun, the central mass accumulating body in our co-rotating protoplanetary disk, sort of has an age that's older than even the calcium aluminum inclusion. But by our definition that we work with, the calcium aluminum inclusion represents T0. And after that, things become evaluated. And in fact, a little bit halfway through the talk, I'll try and say that maybe what we now call the tau accretion age, which is about 62% the mass of the Earth, and that's what we talk about these days, the tau accretion age, or half-mass age. The half-mass age of the Earth, I have recently published, and I've speculated to be 10 million years. And some people say, it can't be that young. Well, if you actually look at that number, you will find that this 10 million year tau accretion age, it just means 60%. When you reach about 99%, it's over 50 million years. So you have to be careful about what you mean by we know the age of the Earth is at least T0 plus X. Because what do you mean? And so, well, my colleagues know what I mean when I say the tau accretion age. That's a calculatable number, okay? Did I answer that? No.
Where the 4.5 billion years comes from?
Well, the 4.5 billion years actually, oh, come here, please. Yeah. See that 1 million year period of time, the 2 million year period of time? It would be in that period when we expect calcium aluminum inclusions to be built. Okay, they're built close to the star. They're definitely built during the protoplanetary disk stage. I cannot define it as anything better than that in time, but that is, in fact, NASA has only recently, last month, been able to image spectroscopically crystals coming out of the central portion of a protoplanetary disk and being splashed out into the outer reaches. That's the first time we've actually seen crystallized silicates being splashed out. So that's how we know that piece of information, okay? And thank you. I'll need your help every once in a while if I have to stay. All right. But back to Copernicus. Isn't it just a clever idea to sort of stare down at the planets and notice they're all going in the same way? Most of them are all spinning on the same axis. It is that simple motion that tells us this story is correct. And that was 500 years ago. And I think that was really an impressive observation. Please. Thank you very much. Next series of impressive observations. Way over there, on the x-axis is the log abundance measured in a rock called a C1 chondrite. I'll use the word chondrite frequently. Chondrite is a meteorite, but chondrite is a special family of meteorites. The chondrites really are cool. They have in them metal and rock. Sometimes the rock is what we call chondrules. They're little droplets about 1 millimeter in size, made up of flash silicate melt liquid. The metal, it's iron-nickel alloy. It is these essential two components, silicate and metal, that make up the rocky planets. These are the building blocks of planets. Okay, so that's an impressive piece. So the CI chondrites is a special family in and of itself. They're the most primitive. They're the ones with the greatest amount of elements like potassium and sulfur, the volatile elements, the ones we have the most difficulties in constraining compositions. Okay, then on the y-axis is the abundance relative to the sun. Well, we can't actually do ppm for the sun, so what we say is, I see the spectrum. I'm going to assume that, that I'm looking at 1 million atoms of silicon from the sun, and I'm looking at 1 million atoms of silicon in CI. So now I can pin that XY point at 10 to the 6, 10 to the 6 for where silicon sits, and I can look at every other element in the two spectrum. And what we can see is an absolutely fabulous, come over here please, youngster. Thank you. This I can't do it at this angle. I'll go upside down. But you can see that must be about 6 orders of magnitude correlation. That's a spectacular correlation. And we can explain lithium. Lithium is actually fusing in the sun. So that's why it's off scale here. What you'll also notice is the noble gases are off scale here. It's because these carbonaceous chondrites don't actually trap that massive amount of helium, for instance. Just think of helium. I mean, 25% the mass of the sun is helium. You couldn't trap that in a rock. It would just make the rock float to the sky. And then the other special are the nitrogen, carbon, oxygen, okay? But it's this rule of thumb that we can use to really understand our star, our protoplanetary disk composition, and our planets. The other thing I think you need to think about is an interesting problem that we still have and haven't resolved, which is called the, I can't think of the words right now, but we know that the solar photosphere, which is the skin surface of the star, it's like this ocean surface, we know the composition of that. And when we use helioseismology through the acoustic sounds that you can pick up of the sun, we can look inside the sun and see that its metallicity is heavier than what we would calculate from the sun's photospheric spectrum. So we've actually sent probes to near the top of the sun, not too close, and the sun is constantly spitting out plasma as well as little rock fragments, tiny rock fragments. And that spit out was picked up by Parker. And that Parker probe actually ended up giving us information in which we can actually look at the magnesium and silicon abundances in that material. And so from the solar winds, helioseismology, and another piece of solar neutrino information, we can put together a story that actually is coherent but not proven, that the inner portion of the sun has a higher Z number or is heavier in its atomic mass than the outer surface of the sun. So that's all we can get from that. Oh, please, the next one. Laser pointer only. Okay, good. All right, I sometimes struggle as to whether I like this diagram first or this diagram, but I'm going to go to this one. So in my business, as a geochemist, I like to talk in parts per million. My friend Afu Lin, who gave a lecture right before lunch, he likes to talk in the number of atoms. So if I want to talk to everybody in the room, I think most of you are chemists, right? I have to really talk about both weight percent, or parts per million, and atom percent. What you see, I want everybody to focus on oxygen. You'd sort of in the top diagram, you see it's about equal amount of oxygen and iron. But if you switch to atomic percent, 1 out of every 2 atoms in this planet is oxygen. That's just an amazing fact. You probably don't think of that. I mean, especially when you think about the core being made up of almost pure iron. But I'll guarantee you 1 out of every 2 atoms in this planet is oxygen. The next thing I think, if you stare at the lower diagram, is there's equal proportion in terms of atom percentage of iron, silicon, and magnesium. And in fact, if you add these 4 elements up, you get to 93, 94% the mass of the Earth, the mass of Mars, the mass of Mercury, the mass of Venus. It's that small difference, the ratio of iron to magnesium, the ratio of magnesium to silica, the ratio of magnesium to oxygen, is what we must determine independently for each of these planetary bodies. We must not assume, we must determine. So for those of you who have not been here during the week, this is what we've been talking about. Please, next one. Oh, good. So about 15 years ago, we were fortunate enough to be funded to go up into the I think it's the J4 position of the Earth. And we were able to sit there for a long time and actually open up our collectors. And we were able to get pieces of the sun and bring them back, bring them into the laboratory, and measure their oxygen isotopic composition. Could we just go back? I should have highlighted over here this portion of the diagram, which is just using the numbers from the previous diagram on the composition of the solar photosphere. You can see that hydrogen's the most abundant, helium, then carbon, nitrogen, oxygen. And that's actually the composition of the gas giants. And then if we go from oxygen to the things above the red line, oxygen, magnesium, silica, iron, that's the composition of the rocky planets. Next slide, please. So oxygen, knowing oxygen is the third most abundant element in our solar system, it means a lot. And knowing that its isotopic composition of the sun, which is way down here, is a long, believe me, that's a long distance away from the oxygen isotopic composition of this planet. And in fact, you'll see that Mars is right about somewhere there. Yeah, we don't plot Mars there, but Mars, Moon, and Sun, and the Earth are all really tightly plotted right next to each other, and a very good distance away from the Sun. Yet again, one more piece of evidence, stop using the photospheric composition to tell you what the Earth's composition is, because this is demonstrating that we're different from that. Next slide, please. So, just a couple of years ago, with a wonderful graduate student I had at Tohoku University in Sendai, Japan, we actually looked at the uncompressed density and the what we would say would be the atomic number for the planets in the solar system, and we found this correlation, and it's been known for a while: Mercury, Venus, Earth, and Mars, and the rest of it's not part of the correlation. But this correlation is actually also works well for the bodies in the asteroid belt. And this is looking at uncompressed density versus distance from the sun. And it really just basically say that the distribution of iron might be controlled by the magnetic field in the early solar system. And so I asked the question, can the magnetic forces overcome the turbulent forces in the protoplanetary disk? And a good friend and colleague who I've always listened to carefully, Dave Stevenson, a guy that's super smart, says never happened. But I also listen to Dave Stevenson about heat flow, and he's not always been right. So, but I'll still listen to him. We don't know the answer to that, but I'm willing to, duke it out and find out what it is next year, the year after, the year after. Because I think that's the healthy state of science, is to push my colleagues to sort of think about it. Next slide, please. But this might actually give us an insight into ion enrichment inwards in the solar system. And in fact, a prevailing model for the origin of Mercury's composition has been to hit it with a big ball of rock and splash that surrounding mantle away. And I didn't like that, but I didn't have an alternative idea until I came up with this one. And I just basically accumulated a lot more iron magnetically at the Mercury accretion distance. Next slide, please. So I'm going to sum this up by saying the biases in the meteoritic record. One, the asteroid belt is really a trivially, there's like 1 million asteroids that are about 1 kilometer in size. Not all of them are kilometers, this is a spectrum, but it's really only, 4/100% the mass of the Earth. It's really it's still even much smaller than the mass of the Moon, much, much smaller. So the asteroid belt is small. The Kirkwood Gap, zones of mass depletion. So for 4.5 billion years, the asteroid belt has actually been excavated due to the gravitational pull between the sun and Jupiter. It's been throwing out material all the time. And so And so the astronomers keep talking about what was the size and mass fraction in the asteroid belt 4.5 billion years ago. And it's just amazing because some people say two Earth masses, and some people, in fact, one of my friends reviewing my paper says, never, couldn't be, but he was an earth scientist as opposed to astronomer. And the astronomer paper that I cite basically says as much as two Earth masses and as little as almost what it is today, you know. They just don't know. It could be possible. Well, of the meteorites, we only actually have meteorites that came to us in the last 1,000,000 years. Even when we go down to Antarctica, those ice sheets are not that old. So every meteorite that we picked up and talked about is really only 1,000,000 years old. Sure, I can point to you that there are, you know, less than a handful of meteorites that have been found in the sedimentary layers of the, I don't know, Jurassic, let's say. I can't remember it, but a long time ago. But what we do with these smashed up, barely preserved meteoritic fragments is say they look like present-day meteorites. All right, and then the other thing I can tell you amongst this meteoritic record, a couple of papers published in Nature just last year says most of them only come from about two crashes in the asteroid belt over the last 40 million years. And that's why we have so many what we call ordinary chondrites and so few of the others, because the two meteorite bodies that were hit were ordinary chondrites. So we're really biased in that sense. And here's the two other ones that are a problem. Lacking silicate mantles matching no NC ions. So we now have, and I'll touch on this ever so briefly, but we got NC and CC. NC, just the inner solar system, CC, the outer solar system. The inner solar system, asteroid belt to the sun, outer solar system, beyond the asteroid belt, okay? How do we define this? Isotopically, the ones out there, beyond the asteroid belt, are distinctive in more than a dozen isotope systems, nucleosynthetic isotope systems. And when you plot them on XY diagrams, there's a gap between what we call the NC meteorites and the CC meteorites. That means they're distinctive at every level, okay? I don't want to get into those details. They're just hoary. But what that last black bullet says is we have iron meteorites, those things that are really nice, heavy, and fun, and easily found by farmers. We have iron meteorites from T0 plus 1,000,000 years, T0 plus 2,000,000 years. But we don't have any silicate rocks from that period. And you don't accrete iron by itself, okay? We've never found evidence for that. So that's a bias. We don't have the silicate surrounding mantles of that material. And now here's the other big bias that I'll put a lot of emphasis on. The NC chondrites, we have not chondrites and chondrites that are NC, not chondrites and chondrites that are CC. So chondrites, again, are the ones that are mixtures of metal and silicate. Not chondrites, which we call achondrites, are differentiated. Iron meteorite, that's an achondrite. Just silicate, that's an achondrite, okay? So an achondrite, you have to get the iron and the silicate together, and then you have a chondrite, okay? So there's a lot of things to keep in mind. But basically, the two things that we can take away is that we're missing half the story from the early days, and that the building block here, the ones that we have, are older than Mars. I'll show you that next. The takeaway story on this one is the yellow. Earth has a chondritic composition, but just not these chondrites. So these two diagrams above, I basically only want to show you that in terms of elements like iron, magnesium, and silica, you can plot all the things that we call chondrites there, and iron's not sitting in, I mean, the Earth is not sitting in the middle of them. That's just a basic story, right? It's a walkaway. All the other chondrites are sitting somewhere, and the Earth is outside. Again, all the other chondrites plus this one, and the Earth is outside. And I plotted this as two different Earths with two different silica contents in the core. because I have my content, somebody else has their content, and I say, hey, it doesn't matter how much you want to put in the core. It's not going to make the Earth look like the rest of the chondrites. Okay? So it's an important takeaway message. The Earth definitely, I can show you why it has chondritic composition, but this alone demonstrates that the Earth doesn't look like any of the chondrites we have. So we also have to be careful. Next one, please. If I look at all of the inner solar system ones in terms of magnesium silica, they don't look like the outer solar system one. Magnesium, silica, iron, and oxygen, the four most abundant elements that make up the rocky planets. So we have to, you know, do a lot of work to get these compositional models for what might be Mars and Earth. And we can't make a simple assumption. So these are, and this diagram over here actually shows, it says reduced. So we can have a very oxidized system. The surface of Mars, it's the red planet. That tells you it's rusted. It tells you it's oxidized. And in fact, Mercury is very reduced. And the Earth is fairly reduced. And these things called EHEL, L means low, H means high, very sophisticated. It just means the amount of iron. And it's on this axis because it has no oxidized iron, no FeO. Everything's Fe, as in the native metal state. So if you look at the solar system, there's very marked differences about the oxidation state of the solar system when it was being built. You have to keep that in mind. Next thing, please. Oh, this is a simple diagram. What I want to show you is we tend to think of them as two kinds of elements. Siderophile is really Greek for iron. Lithophile is Greek for rock. Lithophile are elements that you find in abundance just outside, being rained on right now probably. And siderophile are mostly concentrated in the Earth's core. And when you get a meteorite, such as the ones that are being plotted right here, these are the chondrites. And in the chondrites, you can look at both the iron-loving elements and the rock-loving elements. And you can find that there's a whole bunch that are in equal proportion and a whole bunch where the elements are in equal proportion. We call these the refractory elements. During World War II, the British and the Americans were, as well as probably the Japanese and the Germans, but they were actually running scientific experiments in laboratories to find out, to make jets. And what they were really doing was really seeing how to make the most efficient jet possible. And they were burning hydrogen, and they were trying to see, you know those, when you see the back of the jet, you see the exhaust of the jet. What do they call that? The area where the exhaust comes out. Whatever. But they don't want it to clog up, right? If that exhaust pipe gets clogged up, you have inefficient jet action and it just doesn't fly well. So they were doing thermodynamics, and they were figuring out what will condense at what temperature, because they didn't want condensation. They wanted to have this gas efficiently burn and never condense. And that became the JANIF tables, the Joint Army, Navy, Air Force thermodynamic tables. We still use them today to understand condensation in the solar nebula disk. World War II research being used for science today. And it's those thermodynamic properties that actually helped us to understand what are the refractories versus the volatile elements. Once we knew that, we then started noting that a wide range of meteorites, those from the inner solar system, those from the outer solar system, all have refractory elements in equal proportions. The Earth has the same characteristics. But I just wanted to show you the chondrites. And in fact, we're trying to understand the slope patterns. And I'll get to showing you that in a couple more slides. But it's just that simple pattern. Refractories, volatiles. Refractories, volatiles. That's all I want to show from this. Next slide, please. All right, this was sort of what I did for part of my PhD. So I had a paper that came out Oh, for those of you who are students in this room, so part of my PhD, it said I got my PhD in '88. I actually left the university in '87. So in 1987, I actually finished writing my PhD, then I went off and got examined. I was at my next job already at the Max Planck Institute. And people knew about my chapter 5, and I was nervous. And so for you students, I was really nervous. I was going to publish a paper on the composition of the Earth, and it was going to be on every element in this Earth. And I was nervous. In fact, what really surprised me in the later years was I was encouraged by one of my advisors that later hired me as a postdoc when I went back to Australian National University, Ted Ringwood. He was one of the toughest guys in the business. He had a reputation for mean and blustery. But he helped me get over the emotional hurdle of publishing. And the great lesson I learned is it will never be perfect. So to the students in the room, I will tell you that it will never be perfect, but I'm still glad that I was nervous and supported by friends to really publish. So then I came out with this paper in '95, and in fact, it was my graduate students over the decades who just encouraged me most recently to publish a 30-year review of this paper, which has just come out right now. So it's been a very, very interesting exploration. But this was one of the most important efforts. This is all the compositions for rocks out of the Earth's mantle. And this is the field, roughly, for the melts that are made from these rocks. So what you're trying to do is connect the, let's call it the dots of the melting process. And from those green rocks, you have this blue line, which is when you melt the rock, it has a composition of not melted, melted. And what you're trying to do is calculate back up to here. Now, we all know that what you want to do is go down there because that trend is really nifty. However, I know that this was happening. There was an injection of material a little bit later on. And so I wanted to stay away from that red. So that said, I can't use this whole trend. I can only use half the trend, and everybody knows the correlation goes down. And in fact, the problem there is that the accuracy of your endpoint over here by my hand gets really waffly. But that's what I did in the end. And I published my model. And then a couple of years later, a fellow named Jun Korinaga said, can I have all your data and I'll reinvestigate your model? And then I told him, don't do it. Guess what he did? Yeah, he extended it down to there. But the good thing was he got the same answer as I did, a little bit lower, but within uncertainties, the same thing. So it made me very happy at some level. But I keep telling him it's inaccurate. But you use this kind of information from both the meteorites and the Earth to reconstruct the composition. Please, next. So I don't need you to understand everything on this diagram, but what I'm going to highlight is when I did all of that work, I ended up with a fairly flat trend for the refractory element abundances. And that was sort of, but we could demonstrate that other ways. But I said, that's good. I really felt good about that. I could demonstrate that they were there. Isotope systems have been telling us this for a while, but I was able to match the elemental systems with the isotopic systems, and that really helped me. And then this sort of orangey area, or whatever color it is, oh, the different colors, there they are, rocks, metals, and chalcophile just means it runs around with sulfur, like lead sulfide, that you can think of that. And what you see is their condensation temperature versus their abundances in the rock portion of the Earth, not the core, actually shows a correlation. What does that remind you of? The next slide, please. This. And so this was actually what I would call oh, there it is. The refractories are flat, and the Earth comes down like this. And that was what I would call the volatility trend for the Earth, or what might be the integrated composition for the Earth at one astronomical unit out from the sun. You know, at 1.5 astronomical units out from the sun is Mars. And I can't remember, maybe 1/2 astronomical unit out from the sun was Mercury. Could you just press it one more time, please? So the model for Mars is actually what we did with Takashi Yoshizaki, my former PhD student, and I actually published a model using the same sorts of methodology on the composition of Mars. And I'm really happy we did that together. We had a whole lot of fun. And I can tell you, PhD supervisors have a lot of fun with their students. You know, it was really good. And what I would say the takeaway message for me was that this depletion trend, now this is interpretation, this is not data, it could be early accretion in the nebula. Mars was built before we lost the nebula. We know that the half-mass age for Mars is about 1.9 million years. So probably at least 75% of Mars was built before we lost the solar nebula, or the protoplanetary disk. And so one of the problems we have in these early days is we can't distinguish between space and time. Because there will always be a heliocentric thermal gradient. And there'll be a thermal gradient here through time. And we can't make decisions in that kind of space. But one thing that really made me scratch my head for the longest time was that Mercury has the same potassium-uranium ratio as Mars. And I think just about everybody was surprised that the Ku ratio of Mercury is the same as Mars. We all thought it was going to be very depleted because we all thought that the volatile element of potassium should be really just gone. And my view is that if you accrete when you have a protoplanetary disk, you don't lose so many volatiles, which is a very different perspective from just thinking of temperature alone. Next slide, please. All right, that does the first part of the story. How am I doing for time? 2 hours left? Don't worry, I'll just go at my pace. I'm a bad boy. All right, to continue stories. So in 2005, I received an email from Carl Zemelis, a former editor of the physics section of Nature. And Carl asked me to review a paper. And I said, what? And I looked at the paper, and I sent an email right back, and I said, I don't think I'll do this. And he wrote back, Bill, please do this. All right. I knew Carl a little bit. And so I looked at it, and I wrote back, and I waited a day. I wrote back, and I said, Carl, I don't know what's on the X and Y axis of the diagrams. That's an honest statement. I did not know what the heck was being plotted. And he says, well, we need an earth scientist, and you're probably the most appropriate one to do this. And so one of the good things about university life is you're on committees. And when you're on committees, you're sitting beside another faculty member from another department. And I've actually enjoyed many committees, but not every committee. In fact, I really enjoyed one of the art history professors I met. She made her job sound fantastic. I almost wanted to become an art history person after talking with her every day. But I had a good friend, Jordan Goodman, in the physics department, and I said, well, I'll call up Jordan. I call up Jordan, and I said, Jordan, can I actually work with one of your senior graduate students or postdocs? What's up, Bill? I give him the title, and he goes, no, come right now. He literally, I handed him the paper, and he literally read the first 2 pages of the paper before. Yeah, let's review this together. And so that's how I started my life off in neutrino space, not knowing anything, absolutely anything. So for you physicists, don't think I'm a particle physicist, okay? But both of these are products that I was involved in making, and this one was really interesting. What you cannot see is the words on that thing right there. And it's called NGA. Now, what does NGA stand for? Ready for this? The National Geospatial Intelligence Agency. With no intelligence, right? It's NGA. Yeah. So during World War II, it was called the Mapping Agency, and they used to map the harbor of Japan, Tokyo and various other places. And so this is what they're doing, and they wanted to know probably what was happening in Iran and probably what was happening in North Korea, and I know that to be certain. But I have received a lot of funding. I have no security clearance. I don't, you know, I'm not a spy, a secret agent. I've never even held a gun. But I've received almost 20 years of funding from the U.S. intelligence community. Why? Even Apu doesn't know. That's because we want to look at nuclear reactors, not ours, but yours. Now, I can't remember yours, but it shows up on this map. So I think it looks like it's in Rio. Is it in Rio? Yeah, it looks like it is. See this sort of a dark reddish brown dot? You know, we know about it. And in fact, of course, the U.S. intelligence community wants to know about every nuclear reactor on Earth, or possibly in Earth. A week ago, I agreed to review a paper from PEPI yet one more time, and this may be about my 8th time reviewing such papers. This one is again about a nuclear reactor in the Earth's core mantle boundary. They're always pushing this idea. But the National Geospatial Intelligence Community, the Defense Intelligence Agency, and the CIA have wanted to know what is the reactor spectrum, that is energy versus intensity of reactors. And then the next question, what is the spectrum from the Earth, the natural emission spectrum from the Earth? So I've been paid handsomely over the years so that their subtraction is accurate and precise. So that's why we need to know what is the Earth signal so that we can subtract it and know the reactor signal. On the other hand, I need to know the reactor signal so we can subtract it from the Earth signal. And in fact, the rest of my talk is going to be about the Earth signal, and every experiment that has been done for geoneutrino detection has been funded to look at the reactor signals. So it's really important to get rid of that. So this diagram, which you'll see that there's a whole bunch of dark blotchy spots up on the east coast of the United States, nuclear reactors. Japan, full of the dark blotches, that's nuclear reactors. You can see off the tip of Africa. South Africa has a nuclear reactor. Brazil has a nuclear reactor.
There's nothing in Iran. There's nothing in Iran.
Right, because all we plotted was all of the IAEA admitted reactors.
Sorry, but curious.
Bashir should be up there, though. Just hold my hand. I can really tip over if yeah, I don't see Bashir. The Bashir reactor should be there. I don't know. I cannot give you a good reason why it's not there.
Curiosity, but this is watched from where? From a satellite? How do you collect the data?
Oh, all the data is available. The IAEA.
No, but what is the detector that collects this?
That's calculated.
It's calculated. It's not.
Yeah.
Oh,
It uses a model that I'm going to try and tell you about. And so we use a model for the Earth, and so I'm going to show you that calculation to get to this. This was published in 2015, Usman et al. In Nature Scientific Reports. Next slide, please. So oftentimes, I'm going to hold on to the back of your chair because, all right. I just get dizzy sometimes, and when I tilt my head too back, I'll just fall over. So there are many neutrino sources, and people ask me about that all the time. You know, how do you know the difference between neutrinos from the sun and neutrinos from the Earth? They're very different. The ones from the sun are neutrinos. The ones from the Earth are antineutrinos. I'll get into that in a little bit. But we have nuclear reactors, stars, particle accelerators, supernovas, cosmic rays, black holes, natural radioactivity, and the Big Bang. Yes, there are still neutrinos from the Big Bang. These are called the relic galactic neutrinos. All right, next slide, please. Here's a nice little concept. The Earth has been referred to as a neutrino star. It puts out about 5 times 10 to the 25 neutrinos per second, illuminating the universe with its brilliance. So think of it that way. It's really quite cool to think of. Next slide, please. This excited me. I've been in the business so long that actually Kajita Sensei and McDonough got the Nobel Prize in Physics in 2015. I was up watching the news because we kind of knew that Art was going to get the Nobel Prize. Art would go every winter to spend 3 months at the University of Hawaii. In fact, in 2012, Art had asked me to write a chapter for his volume, and so I got a chance to write it. And I didn't know he was really going to become a Nobel laureate, but it's still kind of fun. I saw Art just last week of October. But yes, in the third slide, it really said geoneutrinos. And boy, I was a little boy again when that happened. Next slide, please. All right, what are geoneutrinos? I need to walk too, that's the other thing. Geoneutrinos are specifically antineutrinos, and solar neutrinos are neutrinos. And I think most everybody understands that we have electrons and we have positrons. And you can think of a positron as an anti-electron in that sense. So that's all we're talking about in terms of the antimatter. And electrons are, first generation matter state, leptons. And a neutrino is a first generation matter state lepton. An electron is charged, a neutrino is not charged. So this is one of these two things, quarks and leptons, are called fermions. So in some sense, there's a uniqueness to neutrinos because they're chargeless. And in fact, in the standard model, they're massless. In reality, they have some mass. It's a finite mass, and it's below a half electron mass, a half of electron volt, sorry. Whereas a electron is a 500,000 electron volts, which already makes the neutrino 1,000,000 times lighter than an electron, which is already 2,000 times lighter than a proton or a neutron. And we still don't know how light they are. In fact, it looks like they're lighter than 300 milli-electron volts. But we're working on that. Now, yesterday I was asked a really fun question. In fact, I scratched my head for the longest time. Why does a neutrino oscillate? And for any of you physicists who are in this room and think about that, being asked why it oscillates is a head scratcher. I can tell you how it oscillates, but I didn't think about the why it oscillates. It's actually, so I wrote to several of my friends, and I got long answers and I got short answers. I like John Learned's answer. He says, because it can. And the reason really is because of its mass. It's approaching the mass of a photon, which he says is 10 to the minus 22 eV. And I can't even think of what that mass is, but these are very distinctive leptons, okay? The Earth is absolutely transparent to a neutrino. A neutrino can travel through a light year's length of lead and have 50% chance of getting out the other side. This is how really quirky these beasts are. I have been on this Earth for 70 plus years. It is likely that either a neutrino has interacted with my body or it hasn't, but no more than one. Okay? And the neutrino flux. My thumbnail's quite like everybody else's in this room. It's about 1 square centimeter. There is 6 million electron antineutrinos passing up through this room every second from radioactive decay per centimeter square. There is 10 billion electron neutrinos coming down straight through us from the sun every second. We are absolutely showered in neutrinos, and we're using them to understand processes in the galaxy. Next slide, please. How does a neutrino, antineutrino in the Earth get generated? Well, when you change a neutron into a proton, as in beta minus decay, rubidium-87 decays to strontium-87, what you're doing is changing the atomic number increase. You actually change a down quark to an up quark. This weak force change engages a W minus boson, which is, you can think of this as like a photon, a force carrier. And magically what you're doing is creating this not pre-existing electron, neutrino, and electron from this exchange. And that's what's happening inside the Earth. Can I have the next slide, please? The Earth science portion of the question. So the overarching question is how much fuel is left to drive the Earth's engine? And I have a fuel gauge here. So for those of you who might own a hybrid car, you would not like to get up in the morning and not know what's in your fuel tank. Do I have enough on either my battery or my petrol to continue driving today? We do not have a fuel gauge. We have no idea, relatively speaking, how much of the initial primordial Earth of accretion, just the kinetic energy, versus how much radioactive energy is left inside the planet. When we do our job to completion in the geoneutrino business, I will give you one of the gauges, and by subtraction, you'll know what the other gauge is. Then this vehicle will have an appropriate fuel gauge. So that's, you can see, is what I'm trying to do, is deliver you a fuel gauge. Next slide, please. This is our current state of knowledge, which says that in the continental crust, we have so much potassium, thorium, uranium, it's about 7 terawatts. In one model of the bulk silicated Earth, we think we might have 13 terawatts, so that 7 and 13 give you 20 terawatts. You'll see in the next slide it will be different than that. Oh, no. It's kind of exciting. You want to know the answer. I have to slow him down. He's very excited. He's got a big smile here. Well, what we can see is the core. I say it's about 9, but I was getting very generous at the time, so I say 4 to 15 terawatts, just to say we're not that sure what is the flux of heat coming out of the core. And then the rest of it is the secular cooling, let's say, the kinetic energy still coming out of the Earth. All right, so that's the basic heat story. And the number 46 plus or minus 3 has been a number that's been with us for over, about 60 or 70 years, I think. From the 1950s when Harold Urey first put out his number. So next slide. It's been with us for a long time. So this is an interesting plot because in the blue circle over there on the left, I give you the radioactive story. But some of my colleagues have their own model for the Earth. Oh my gosh, there's controversy. So what we call it is low Q, middle Q, and high Q, standing for heat flux. Some people think we only have 10 terawatts of radioactive energy in the Earth. I think we have 20 terawatts of radioactive energy. And other people think we have 30 terawatts of radioactive energy in the Earth. We don't know, and that's what our job is, to sort of demonstrate which value is more appropriate. Next slide. And if we don't demonstrate it, we're left with this problem. Silicate Earth model differ by a factor of 3. Is it 10, 20, or 30? But if you say it's 10 for the whole silicate Earth, and we know that the crust is 7, there's only 3 terawatts in the mantle. If you say it's 30, it's 27 terawatts in the mantle. If you add the uncertainties, there is a factor of 20 between all our models. That's the kind of level of uncertainty we're dealing with. Next slide, please. All right, this is an easy equation. First, advance, please. This is telling us a flux. And this flux depends upon just certain parameters that are going to be relatively easy to identify. A is essentially a constant. It's the decay constants and molar number, et cetera. Next slide. Volume of the source unit. The source unit is called the Earth. Next slide. The abundance and density of the source unit, and really that's a geological term. How much uranium or how much thorium? And what is the density in the crust? What is the density in the uppermost mantle, lowermost mantle, the core? Next. The distance between the source unit and the detector. Well, the detector that I'm working with right now is the one that's in southern China, and we are having radioactive decay in Brazil. That's one distance. So any atom that's going to decay has the potential to be detected in southern China. Next one. The survival probability function. That is purely a particle physics piece of information. Next slide. So as a geoscientist, we have to put into this equation Earth structure, density, distance, and chemical composition. That's our job. Let's get ready to work, okay? Next slide. All right, we have to voxelate the Earth. Okay, so we construct a 3D reference model, and that's what I've been doing for 20 plus years. Constructing 3D reference models in which we have voxels, in which we put in seismic VPVS density and chemical composition. I actually assign what will be the concentration of uranium and thorium. Now for a 1 by 1 degree grid tile that might be 3 kilometers thick in Brazil, my uncertainties on that don't give a hoot. The probability for decay happening here being detected in Japan, China is really small. So what happens is when I get to within 250 kilometers, I change my grid scale. That's obvious, right? But next slide. And so this is showing you the details. I just wanted to show you, we're trying to put in all the numbers, all the uncertainties. You don't need to read any of the numbers, but you can get a sense, a flavor of what's going on. We put a bunch of layers, we define them for the continental crust, the oceanic setting, the depleted mantle, and the gridding of the Earth at the 1 degree scale, 1 by 1 degree, and then we have tiles, because they're voxels. And in the top of the Earth, it's about 3 kilometers down to the moho, and then it jumps to about, I think about 50 kilometers for lithospheric mantle. Then it jumps to big numbers when we're talking about the depleted mantle and the enriched mantle. The further, these detectors have resolution of 1 over r squared. The further I walk away from the detector, the less I can see it, okay? So that's what we're doing. That's perfect, you know, go right ahead. Advance. We have 3 components. What we call the NFL, which is the near field lithosphere, right next to the snuggly guys right up by the detector, out to about 250 kilometers. We put an enormous amount of work into what is the geology at that distance. And then next slide, it's just going to be a bar. And we want to know what the far field is. And then we can see that for the lithosphere, 50% from the near field, 25% from the far field, and about 25% from the mantle. And usually we talk about the enriched and depleted mantle, but we always have to be aware of the other mantle. For instance, we've been spending a lot of time talking about early Earth differentiation volumes or masses. We're talking about stuff at the bottom of the core that may be enriched or not enriched. And we're also talking about the core having radioactive elements. All these have to be tested. Next slide, please. So this is the current, this is really, I'm trying to get to a status report. So the Japanese experiment was the first to get online. We have 20 years of data from that. The Italian experiment, Borexino, is finished. The SNO Plus experiment in Canada is counting. It's been counting for 3 years. It actually came out in November with its latest value. We're really excited. I'll show you that data point. And the Juno experiment just started counting. The Camland Japanese experiment is a kiloton scale detector at 1.5 kilometers underground. The Borexino Italian experiment was 1/3 of a kiloton, 1.5 kilometers underground. The SNO Plus, a kiloton experiment, 2 kilometers underground. And the further you're underground, the better your background is, because the muon's coming through. Juno, 20 kilotons. It turned on at the end of August. Already it has more counts than the other 3 detectors in their lifetime added up has. I can tell you right now that in June, we are going to report at the Neutrino 2026 meeting the number of counts that we have detected for the Juno detector. And I'm promising you it's going to be a game changer in earth sciences. We're really going to know that number quite well. What is the radioactive power of the Earth? So that's the newest experiment. The CJPL, well, we haven't gotten that funded yet, but we would like to get it funded, completely funded. It has 2.4 kilometers of overburden. That means it has negligible, zero background. It's really a beautiful site, very far from nuclear reactors, and should be a really wonderful location for detecting neutrinos. And interestingly enough, the distance between Camelan and CJPL is equal to the distance between the surface and the core mantle boundary. Next slide, please. All right, I'm getting to the end. I'll just say that the y-axis is a physics measurement. The x-axis is a geological model for the crust. The intercept is the mantle value, how much is left in the mantle. The slope is 1 because it's a 3-component system and only 3 components. And so each data point represents the slope of 1. Okay, it's already fixed. And so far it looks like it's 9 TNU, which is terrestrial neutrino units, that can be translated into TW, and the answer looks to be about 20 terawatts, plus or minus sort of 7 to 8 terawatts. And what we're hoping is to really knock that number down to 5 or less terawatts. Next slide, please. 2 speculative ideas. For about 20 years now, I've been trying to really float the idea of a mobile neutrino detector that would be taken out into the middle of the ocean, sunk to the bottom of the ocean, be 3,000 kilometers away from South America. I like you guys, but I like to be away from you. 3,000 kilometers away from Australia. I've lived there for 10 years and I like that place. But I'd also be 3,000 kilometers away from the core mantle boundary, and my signal would be the mantle, not the continents. And then that, too, would be an independent mantle measurement for its value. That's an expensive experiment, and that's not the only thing. I'd like to go up to the northern Pacific, the mid-northern Pacific, the central Pacific, the southern Pacific, and close down to Antarctica. Why would I do that? Because I want to map out the chemical heterogeneity in the mantle. I want my device to be the first time we map out the chemistry of the Earth's interior, as opposed to seismology always getting the credit for the structure of the mantle. Next slide, please. Oh, I don't know whose model this is, but it's on a Delta VS. Yes, this is Jeroen Ritsema's seismic model. I think you have an idea of why I might want to know what might be a good measure. So earlier in this conference, we were really talking about trying to define the mass and volume of this red zone. Next slide. The reason is because I will calculate how neutrino bright it is. So if I'm up by Alaska and I'll stop 6 times from Alaska to Antarctica with my device and try to see where the uranium is inside the Earth, I'd like a better number for the volume of what we are calling the LLSVPs, or for those of you who's not been in the room. I see the red, I want to know its mass. And then I'll tell you how neutrino bright it is. And I'd like to do that before I go there and measure it, because I'm a big believer in predicting things before doing it. Next slide, please. Final thought of the day. What I can do on the x-axis here is 0 to 15 million years after T0. So in the first 15 million years of Earth history, I can tell you how much heat was generated by radioactivity. And what you can see is aluminum-26 put the Earth on fire. So Stefan was talking this morning about we probably had a basal magma ocean, and he likes the idea of a surface magma ocean. And then when it came to question time, I told him I liked those two ideas. This is one of the reasons, because we had iron-60 cooking the core, we had aluminum-26 burning the silicate earth. That's really, and you know, aluminum-26 half-life is only 0.7 million years, but look at how powerful it is for almost 10 million years. It's because there's so much aluminum in the earth in the early, you know. Next slide. This is a pattern, this is really looking at, this is the model for how the Earth's radioactive power has decayed through time. And I want to have people like John and Stefan who look at this sort of power problem for the Earth and tell me about the Earth's cooling history. And this is the last science slide. And I think that we need to get together the people who can tell them about what is the radioactive power over the last 4.5 billion years. This is it. Now, how does this compare with how fast we have dissipated the kinetic energy of the Earth? Conclusion slides, please. The inner solar system is different from the outer solar system, and we have to be aware of biases that we have identified. But I think we're putting together a pretty coherent model for the Earth, and from that we can actually define its composition. Neutrinos have come along in the last 20 years, and they have helped to confirm that the absolute concentration of the refractory elements, the ones like this, not like this, the ones like that, are at 2.5 to 2.7 times C1 chondrite. That means that they're not here, they're a little bit up there, and they confirm the models that we've built previously. So there is a coherent answer between neutrino measurements for the Earth and geochemical evidence for the Earth. Thank you.
Thank you very much. Time for a few questions.
Open the doors, it's too hot in here.
Great talk, thanks. It was great. I just have a question for, with the previous slide, in fact. Of course, aluminum-26 and iron-60, they're very important in the early stages of the solar system when they're still there. But it seems to me that in terms of timing, that's more at the planetary embryo stage, when the Earth, the building blocks of the Earth were like Mars, maybe. But then, of course, the whole thing is kind of reset by the giant impacts that leads to the Earth, right? So, they are important to make the iron meteorites, for example. Without aluminum-26, probably there's no iron meteorites. But then, for the last stage, that really set the set for the evolution of the Earth. It's pretty much gone, I think, right?
Yes. So for those of you who are not involved in this business, I've given a very simple story, and we can all pretty much hang our hat on that story that occurred. But what I think is almost inescapable, the origin of the Earth's moon is really best explained by a large impact. And that's in part because we're tilted, the moon's tilted, we have a coherent Earth-Moon orbital system, and it really has to be explained, and the best way to explain it is by a collisional process to tilt it and keep it just a little bit off the ecliptic. And if we have that, then what Stefan is highlighting is that's a reset, and I would agree. Here's the next problem. We don't know when it happened. Now, that's why we're going back to the moon. We're going to learn a lot more. And one of the things that we've learned recently by the Chinese exploration has been something that surprised the heck out of all of us. There was magmatism on the moon 2 billion years ago. And after the Apollo astronauts came home, we basically found out that there was a big volcanic party on the moon between 4 billion years ago and 3 billion years ago. And we were happy with that. We thought that this small little body in space went to sleep. Well, it didn't. And in fact, just a couple of expeditions by the Chinese bringing back less than a handful of rock have actually opened our eyes again to really new processes. Right now, there are some people vigorously arguing that the giant impact happened 150 million years after T0. That has one consequence. There's a smaller but yet committed group that's saying it was maybe only 50 million years after T0. That's a healthy state right now. Now, what my information can do is tell you the starting conditions for that either 50 or 150. You know, how soft or how stiff was the Earth when it was hit by this giant impact and shed off a mass that then co-rotated to form the moon. And I think, I like what I can show you, but Stefan's, importantly pointing out that there was a reset. But I think the consequences for whether the reset was at 50 or 150 becomes significant in terms of the rheological properties of how fast the Earth recovers after that moment.
Hi, Bill. Thank you so much for trying to communicate with us here. So you mentioned about you want to know the volume of large low shear velocity provinces that would actually allow you to constrain geoneutrino and heat source in the Earth interior. But shouldn't you also need to know the composition and thus the kind of the incompatible element of uranium, thorium, potassium partitioning into that reservoir?
Which reservoir?
The large low shear velocity provinces reservoir.
Yes. Could I go back? You know the thing that looks like two pieces of eggs on the surface of the Earth? It's about 2 diagrams back. Yep, that one. So what you can think of is there's just 2 entities there. There's the LLSVP, large low shear velocity provinces, or as somebody has called them, 2 pillars in the mantle. That's a good term to just identify. And not 2 pillars in the mantle. So you can think of it as component A and component B. Component A is the thing we call LLSVP, and component B would be the rest. And so when we built this model, this is published in a 2013 EPSL paper, we produced 28 models. And those models are all available. About 5 of them are published in the paper, and the rest of them are in the supplementary. And in those 28 models, we actually have a couple of different volumes of the LLSVP, and we basically have a couple of different models for the contrast between component A and component B. And the one I like best is this one, where the concentration of uranium, thorium, and potassium, they're all 10 to the 4 and 4 ratio, is 5 times the mantle, the component. There's a factor of 5 difference. So if the depleted mantle, or the source for mid-ocean ridge basalts, has approximately 5 parts per billion uranium, which is what's been argued by one of my colleagues, Vince Salters and Andreas Straka. They've published a paper that says that the mid-ocean ridge basalt source region has 5 parts per billion. If it's a factor of 5, the other one only has 25 parts per billion. So these numbers can be assigned and tested and give you diagrams. And so the paper, Shramik et al. 2013 that we have up here, provides you with 28 different models you can look at. Yeah, we just don't want to test one. Go ahead, Romy. Oh, sorry, Suzanne.
Yeah, simple question maybe. So you said something that implied that most iron meteorites are found by farmers. So, and then you said the counterparts are missing, right? The silicate mantle representation is missing. But how would a farmer know that a silicate rock in their field was a meteorite?
Right. Well, I worked at the University of Maryland for 25 years, and I cannot really guess what the number is, but I think it's between 10 and 15 has at least come to me. Residents of the state of Maryland has come to me, and I know that Rich Walker and Jay Kaufman and Rick Arevalo and Phil Piccoli have had almost all these same experiences because we're the kind of guys that look at the rocks. And so you get that kind of number, and none of us have ever seen a meteorite. So every one of them brings us pieces of metallic slag from when people used to make their own farming tools. If you have a meteorite, and this is what we tell them all on the telephone, the first thing to do is to get a magnet. Does it stick to a magnet or not? And I don't know why they'd never do this, but they have their hopes that it's a meteorite, and that's the first thing we do is we put a magnet on, boom, it doesn't hold a magnet. It's not a meteorite. Every iron meteorite is very magnetic. Now, identifying an achondrite that's a rock, that's almost impossible. So, it really is tough to tell. Right. But let me tell you about what happened in 1975. In 1975, the Japanese sent a bunch of their NASA-like scientists down to Antarctica, and they went and collected meteorites at where the ice comes up right at the trans-Antarctic mountains. And that was a game changer in and of itself. Today, we have more than 75,000 meteorites in our meteorite collection. And it was probably only a few, maybe not even a few thousand, maybe only 1,000 or 2,000 meteorites in our collection in the past. And then we went to Antarctica, and we go to Antarctica every year, and it's not just the Americans, it's a lot of countries. And we get lots of meteorites out of Antarctica. So we actually have a nice sampling from that. But even after doing that, 80% of the chondrites are ordinary chondrites. 80%. And 10% represents carbonaceous chondrites plus enstatite chondrites. And then 10% represents all the others. And that's what we call, that's the statistics. But if we were to just say prior to going to Antarctica, it was about 80% iron meteorites. So you can see what changed.
Last question.
Yes,
Hello,
Rami.
Bill. Thanks so much for the talk. It was brilliant. And yes. Anyway, I will be back to the potassium things and following the Stefan as well. So, I could think you showed us in the previous maybe the last slide or before the last slide, you have this kind of a 24 the influence of the element, for example, in terms of the temperature, it's going to freeze it's going to hit the earth and things. And I'm still thinking, because we were talking for a long time ago and keep talking about this contribution of the potassium, because the potassium could be underestimated, and it could produce heating, and it could produce neutrinos as well. Maybe it's too crazy what I'm going to say, but maybe during the impact of the moon, impact of the Earth, we got a dramatic change in everything here, because I keep thinking that somehow, because the moon is very depleted in the alkalines, so maybe during this impact, some kind of heterogeneity happened in the Earth because of this kind of splash. And I keep thinking, I don't know why, that the potassium could be underestimated, and it was a topic in science for a long time, but now it's over maybe. And I keep thinking, what do you think about this currently?
Well, for decades, people have been suggesting that there's potassium in the Earth's core. Ramamurthy, really quite a clever fellow, had a paper in Nature, and this published paper is a result of some experiments he did. And what he did was to take an iron alloy and sulfur and potassium and showed that potassium entered into this sulfide phase, which entered into the metal phase. And from there, he argued that potassium is in the Earth's core because he could do that. And he could show that potassium went into the metal system. And I said, you're right. This experiment shows that potassium will go into the metal under these conditions. Has no application on the Earth whatsoever, I said also. Has no bearing on the Earth because the Earth didn't have 30 weight % sulfur. It didn't have, I think, something like 2 weight % potassium, and it really lacked the silicate sphere. So what petrologists do, and they must remember, is they create plausibility systems that need to be tested and verified by what are the other consequences that would accompany such suggested experiments. And I think it's very important that they challenge any dogma that comes out of me or anyone else, because we all need to be cross-checked, and I think that's an important point. And I would tell you that I've been cross-checked for many times on this topic. And in fact, Alex Cornier, who got his PhD with Bernie Wood, worked at the Carnegie Institute in Washington, D.C., now works in Chile. Together we developed an experiment which we tried something more analogous to the Earth system with a lot more silicate, a lot less potassium and sulfur, and we couldn't get potassium into the metallic state. Made us conclude that it is unlikely that potassium is in the Earth's core. That didn't prove it is or isn't. It just said under these conditions we can't get it in. So I hope we've got our potassium story correct, but I live in fear.
Okay, so I think it's time to wrap up. Let's thank William again.